Okay, so we're continuing our discussion on temperature and pressure and the way it affects the volume, specifically of gases, because gases are compressible. When we apply pressure to them, we can affect their volume. So that's Boyle's law. Boyle said that if we increase the pressure, and again, I like to visualize this with pressure pushing down on a balloon, let's say. And if we increase that pressure, so pressure goes up, then the volume will go down. They are inversely related to each other. And we've been talking about how when a material excuse me, is relatively cold, its molecules are close together, and as it heats up, those atoms, they move farther apart and therefore take up more volume. So the relationship here is that as temperature goes down, volume goes down, and as temperature goes up, volume goes up. So combining these relationships together, we get this. This little symbol here means proportional to. So pressure times volume is proportional to temperature. So if we keep the temperature, excuse me, if we keep the temperature constant, and we look at the other two, if we make the pressure go up, the volume is going to have to go down. Let's just say this was like 2 times 2 equals 4. And we keep the 4 constant. Let's say we make the 2 go up to be 4. Then this is going to have to go down to become 1 so that the relationship remains true. 4 times 1 is 4. So if we keep temperature steady, pressure goes up, volume goes down. That's what Boyle said. Okay, and if we, for instance, keep pressure at a constant, how are volume and temperature going to relate to each other? Well, if the volume goes up, the temperature goes up. Okay, and that's what we've said over here. And then if we keep the third one steady, if we keep volume at a constant, then when pressure goes up, temperature goes up. And as the pressure goes down, the temperature will go down. And so this you may have experienced, this relationship between pressure and temperature, you may have experienced when you've used maybe an aerosol can, or if you play paintball with compressed air. When you've got that aerosol can, and the contents inside the can were under a high pressure, but then you're spraying it out and the pressure is dropping, the temperature also drops. It's very cold, the aerosol that comes out of an aerosol can. Like if you have a can of compressed air used for cleaning electronic equipment or keyboards and stuff, that air coming out of the can is very cold. So the relationship here is a direct relationship, a direct proportional relationship, so that if the pressure goes down, the temperature goes down. If the pressure goes up, the temperature goes up. And that relationship you may have experienced if you like to cook and you use a pressure cooker. With increased pressure, you can increase the temperature and cook food faster. So putting this all together, we get this relationship that P times V is proportional to T. We can add one more thing to the equation here, and that is M. So we can add mass to this equation, and that makes sense because, like for instance, if we add more stuff, if we add more mass, that's going to cause the volume to go up. So the relationship remains intact. If the mass goes down, the volume would go down. If the amount of stuff goes up, if the mass goes up, and we somehow fix the volume, well, that's like stuffing more stuff into a container. That's going to cause the pressure to go up. So the relationship between the variables remains the same here if we introduce mass into the equation. Let's look at another thing that will tie into this here. We'll circle back around to that relationship here in a little bit. But let's introduce this idea of a mole. So a mole is basically a number. It's a really big number. So you could say you have a mole of anything. You could have a mole of pencils. So it's a number that used to describe a lot of things, but it's a rather special number because it relates the atomic mass of an atom to a mass in grams. So, for instance, if I bring up information from a periodic table here, hydrogen has an atomic weight of 1, approximately 1, right here. So its atomic weight is 1.008, so pretty much 1. So if we had an H2 molecule, 2 of them, multiply this by 2, it would be approximately 2. So one, excuse me, one H2 molecule would have a mass of 2 atomic units, but if we had a mole of them, its mass would be 2 grams. It links together the atomic weight and the mass in grams. And if we look at neon has an atomic weight of 20 approximately atomic units. And so if we had a mole of neon atoms, it would be 20 grams. And if we had a mole of carbon dioxide, CO2, that would be 1 carbon atom, 12, and 2 oxygen atoms, which is about 16. So 16 times 2 is 32, plus the 12 from the carbon equals 44. So if we had a mole of CO2 molecules, it would be 44 grams. So what is this big number that I've been saying? That a mole is just a really big number. What is it specifically? Well, it was Avogadro who came up with it, and it is this, 6.02 times 10 to the 23rd. That's how many things are in a mole. So if you've got a mole of pencils or a mole of books or whatever, you've got a mole of carbon dioxide molecules, you have 6.02 times 10 to the 23rd. So if I jump back here to the previous slide, so what we're saying is if we had 6.02 times 10 to the 23rd carbon dioxide atoms, it would have a mass of 44 grams. And again, carbon is the basis of the atomic unit, or the atomic mass unit. And so a mole, 6.02 times 10 to the 23rd carbon atoms, would have a weight of exactly 12 grams. So we had before this relationship that P times V was proportional to T. And what we weren't taking into account with that is how much stuff are we talking about? Because that will affect this relationship as well. And on an earlier slide, we had introduced mass here in this place. So PV was proportional to mass times temperature. But instead of looking at mass, we can instead put in that place, in that little slot there in the equation, N times R, where N is the number of moles. So we can have 1 mole, we can have 2 mole, we can have 1,000,000 moles. So whatever the number of moles is, that goes right in there. That's going to describe how much stuff we have. And R in this equation, R is the universal gas constant. And it can take several different forms depending on the units of the other variables in the equation. So it can be 8.314 joules per mole Kelvin. It can be 0.0821 liter atmosphere per mole Kelvin. It can be 1.99 calories per mole Kelvin. So you'll notice that the mole Kelvin is constant. So when we're using this ideal gas law, the temperature is going to have to be in Kelvin so that it'll cancel out. N is the number of moles, so it will cancel out. And then we're left with basically our choice of either joules, liter atmospheres, or calories. And our choice is basically determined by what we have here on the left side when we have pressure and volume. So pressure might be in newtons per meter squared, and volume might be in cubic meters. So that's going to cancel out with 2 of those, and it leaves Newton meters, which is equivalent to a joule. So depending on our units of pressure and volume, if we are dealing with newtons per meter squared or pascals and cubic meters, that's going to give us joules. If pressure is given in atmospheres and the volume is given in liters, we'll use the second one. And if we're dealing with calories, which is something that we haven't dealt with yet but will, then we'll use this one. So you just have to keep in mind that R is a constant, but it can be in one of these 3 formats here. So it's one of these 3 numbers, and it really just depends on the given problem. What units we're using will determine which of these constants we're going to use. So one more thing here to introduce when dealing with the ideal gas law is this idea of standard temperature and pressure, or STP. So if gases are going to fluctuate in their volume at different temperatures and different pressures, it's often helpful to have some sort of a benchmark or baseline temperature and pressure to deal with. So there is a standard temperature and pressure, or STP, and that temperature is equivalent to 273 Kelvin. And again, when we're dealing with the ideal gas law, we always want to use Kelvin. So 0 degrees Celsius is equal to 273 Kelvin. We'll use Kelvin. And then the pressure, again, depending on what units we're using, can be exactly 1 atmosphere, which is equivalent to 1.013 newtons per meter squared, or 101.3 kilopascals. We're also going to deal with a mole. 1 mole of an ideal gas is 22.4 liters.